Hello everyone. Kotungwane, the native god here. Right. On this lesson, we are going to be looking at work done, energy, and power. Right. Now, before going through this lesson, you must have gone through the lesson on, excuse me, what is this? Newton's laws of motion. Right. Which, if you look at my playlist, it comes just before this one. Right. So if you landed on this video and you haven't watched the lesson on Newton's laws of motion, stop this video and go to the lesson where I cover Newton's laws of motion, right? Because to fully grasp the concept of work done, energy, and power, you need to have understood the laws that govern the motion of objects, which is Newton's laws of motion, right? Otherwise, if you've watched that lesson, then you've landed on the right place. Now let's first look at work done. All right, now work done, the units of measurement of work done is joules. So the J stands for joules. All right. Now what is work done? All right, so work done refers to an action that occurs when an object displaces upon application of an external force. All right. From a practical perspective, if say you need to move a table, right, along the horizontal plane, all you do is you push the table, right? So the pushing of the table is the external force that I'm referring to here. So as you apply that force, right, if the force you apply is enough to move the table, as the table moves from where it was to where you want it to be, right? So say you have a table here and you move the table up to there, right? So you apply a force here and the table displaces from this point to that point, right? So when that happens, that is when work is done, right? So the explanation or the definition of work done is exactly that, right? You can look at it from a practical perspective. When you apply a force on an object and the object displaces, that is essentially what work done is. All right. Now, we denote work done with the letter W, right? And work done, the general formula for work done is force times displacement, right? So from this formula, the W, as I said, stands for work done. The units of measurement for work done is joules, right? The F stands for force, which is in newtons, and the S stands for displacement, which is in meters. All right. Now let's look at energy. All right. Energy is also measured in joules. Right. And energy is essentially the ability to do work. Right. How we define energy is simply that. Right. It is the energy. Right. The energy is the ability to do work. Right. Now we get different types of energies, right? Actually, work done can also be regarded as some form of energy, right? Now the typical types of energies that we get is kinetic energy as well as potential energy, right? Now as far as kinetic energy, right, kinetic energy can be defined as the energy that an object possesses due to its motion. Right, so if you have an object and it's in motion, right, it is going to accumulate kinetic energy, right? Right, either it's going to accumulate kinetic energy or it's going to lose kinetic energy depending on if the object is accelerating or if the object is decelerating. So if it's accelerating, it's going to accumulate kinetic energy. If it's decelerating, then it's going to lose kinetic energy, right? We use EK, right, to denote kinetic energy. So EK stands for kinetic energy. The formula thereof is equal to half mv squared, where EK is kinetic energy, m is the mass of the object in kilograms, and v stands for the velocity in meters per second. All right. And then we get potential energy. Potential energy, right, is the energy an object possesses due to its height from the reference plane, right? So that is to say that with potential energy, for an object to accumulate or to have potential energy, it has to be moving along the vertical plane, right? Or maybe not moving along the vertical plane per se, but it has to be at a height h from the reference point. Now, normally the reference point is the ground, right? That is why we say that potential energy is the energy an object possesses due to its height from the reference plane, right? So if you have an object, right, you have an object, say that's the ground, right, and say you throw an object vertically upwards, right, to some height, right? Now the potential energy as the object, right, moves from the ground, right, to its maximum height or to the maximum point that it will reach before it goes back to the ground, right, it gains potential energy, right, and that is attributed to the object gaining height as it approaches the apex, right? So that is what potential energy is. Now, as far as how we denote potential energy, right, we denote it as EP, and EP is equal to mgh, where EP is the potential energy, m is the mass of the objects in kilograms, and h is the height of the objects above the reference plane, right? Now this we are going to, or I'm going to explain further when we look at the free body diagram of how we look at the energy or the conservation thereof, right, for an object or of an object, right? Now we look at the concepts around conservation of energy, right? Conservation of energy states that energy cannot be created or destroyed, but can be changed from one form to another. All right, and I'll explain just now how that happens. But how that happens is through mechanical energy. Right? That is why it is important to look at the concepts around mechanical energy as well. Because the conservation of energy, right, the conservation of energy incorporates mechanical energy. Now, what is mechanical energy? Mechanical energy is the sum of, or is the sum of an object's energy anywhere along its motion when it moves along the vertical plane. All right, and then EM is how we denote mechanical energy, and mechanical energy is equal to EK plus EP. Right, hence we say there mechanical energy is the sum of an object's energy anywhere along its motion when it moves along the vertical plane. Right, so along the vertical plane we get kinetic energy as well as potential energy. Now we are going to see how mechanical energy relates to the conservation of energy, or how we use mechanical energy as it relates to the conservation of energy. All right, now let's consider this free body diagram, right, where this here represents the reference plane. We also can refer to it as the bottom, right, and this represents the top or the apex or the maximum height that the object reaches before it goes back to the ground. Right, now let us look at the energies involved when an object is projected upwards, right, or when an object, as long as the object is moving along the vertical plane, right, we're going to look at the energies involved when an object is moving along the vertical plane. right? And obviously at the bottom, the potential energy is equal to 0. Remember what potential energy equals to, or what governs potential energy, right? Potential energy is equal to mgh. So as long as the h is equal to 0, right, which at the bottom, the object at the bottom hasn't necessarily accumulated some height because it's still at the bottom. So if the h is 0, it means the potential energy is 0. Alright, so now as far as the kinetic energy, when the object is projected, as soon as it leaves the reference plane, the reference plane, right, that is when the velocity is at its maximum. Right, when the velocity is at its maximum here at the bottom, as soon as the object leaves the reference plane, that is when the kinetic energy is also at its maximum. Remember what the kinetic energy equals to? Kinetic energy is half mv squared. The mass of the object remains constant. Right, so what really governs the kinetic energy is the velocity. So because the velocity at the bottom is at its maximum, it means the kinetic energy at the bottom is also at its maximum. So at the bottom, the potential energy is equal to 0 and the kinetic energy is at its maximum. Now as the object, right, approaches the maximum height, because g, which is the gravitational acceleration, is opposing the object's motion, what tends to happen is that the object decreases in velocity as it approaches the maximum height. Right, that is why the velocity is at its maximum as soon as it leaves the reference plane. Right, as soon as it leaves the reference plane, that is when the velocity of the object is at its maximum. And then as it approaches the top, the velocity changes, and it changes why? Because of gravitational acceleration. So because the velocity, or the direction of the velocity, or the direction of motion is going against gravitational acceleration, that is why, right, as the object approaches the top, the velocity decreases. Right, when the object reaches the top, before it goes back to the ground, the velocity at the top is equal to 0. Right, as soon as it reaches the apex or the maximum height, before it falls back to the ground, the velocity is equal to 0 at this point. Hence, the kinetic energy at the top is equal to 0. And then, having accumulated the height h from the ground, right, having accumulated a height h from the ground, right, at maximum height, that is when the potential energy is also at its maximum. So at the top, the kinetic energy is equal to 0 because the velocity at the top is equal to 0. And then the potential energy at the top is at its maximum. Why? Because the object is at its maximum height. Right? Now, if you look here, using mechanical energy, right? Remember I said we are going to make a relation as to how mechanical energy, right? How mechanical energy influences the conservation of energy, or how the two relate to one another. Right? And how they relate is that when looking at an object that is moving along the vertical plane, so this only applies for objects moving along the vertical plane, right? For objects moving along the vertical plane, the mechanical energy between any 2 points in the object's motion along the vertical plane is equal. Right? I must say that again. The mechanical energy between any 2 points along the object's motion, right, in the vertical plane is equal. Right, so the mechanical energy, for instance, if the mechanical energy between any 2 points along the object's motion is equal, it means that when looking at the top, when looking at the bottom and the top, right, we are able to say that the mechanical energy here at the bottom is equal to the mechanical energy at the top, right? Even when, say, you look at, say, this point, call this point 3, right? If the mechanical energy between any 2 points is equal along an object's motion on the vertical plane, it then also means that the mechanical energy at the bottom, which is at this point, is also equal to the mechanical energy at point 3. Similarly, the mechanical energy at point 3 will be equal to the mechanical energy at the top. So that is what we mean by the mechanical energy between any 2 points in the object's motion along the vertical plane is equal. Right? Now let us use the bottom and the top. Right? So mathematically, remember I said the mechanical energy between any 2 points along the object's motion is equal to, or is equal. Right? So we mean, let us take this point and this point. Those are 2 points along this object's motion. Right? The bottom and the top. Looking at those 2 points, we then say the mechanical energy at the bottom is equal to the mechanical energy at the top. Now, what is mechanical energy equal to? Mechanical energy is equal to EK plus EP, right? Remember this, right? Mechanical energy is equal to EK plus EP, right? So if this is equal to that, it means that the EK plus EP at the bottom is equal to EK plus EP at the top. The mechanical energy between any 2 points in the object's motion along the vertical plane is equal. Right? Now remember that we had already established that at the bottom, the potential energy is equal to 0. So that's equal to 0. And then the kinetic energy at the bottom is at its maximum. So we do have a magnitude of kinetic energy is equal to, now at the top, we also established that at the top, before the object goes back to the ground, the velocity is equal to 0. Hence, the kinetic energy at the top is equal to 0. And then in terms of potential energy at the top, because the object has accumulated a height h from the ground or from the reference point, right, and has reached its maximum height, right, at the top, the potential energy is at its maximum, so you have a value of potential energy at the top. And then essentially, if you get rid of the zeros, it therefore means when looking at the mechanical energy at the bottom being equal to the mechanical energy at the top, essentially this is what it comes down to, right? Kinetic energy at the bottom is equal to potential energy at the top. Right? When you look at that from the perspective of conservation of energy, right, it means that if you look at the object's motion along the vertical plane, right, from here, right, going to the top, the velocity is being lost. Hence, the kinetic energy is being lost. Right? But the kinetic energy is not being destroyed. Right? It is actually being converted. So as the object moves from the ground or from the reference point, right, to the apex, essentially what tends to happen is that the kinetic energy is converted into potential energy. Right? So as the object approaches the apex, the kinetic energy, right, is transformed into potential energy. right? And that is how mechanical energy relates to the conservation of energy, right? This here is proof that energy is not destroyed, but instead it is transformed from one form. At the bottom, it is kinetic energy, and then at the top, it is transformed to potential energy. Similarly, when the object moves from the top back to the ground, right, as the object loses the height, right, its potential energy, right, from the top going back to the bottom is transformed into kinetic energy. Right? Right. Now let's look at the work energy theorem. Right? The work energy theorem states that the net work done on an object is equal to the change in its kinetic energy. Right? That's the work energy theorem. With the work energy theorem, essentially you can look at it from a practical perspective as well. So I'll use the example I used at the beginning. That's when you apply a force on a table and the table displaces, essentially work is done. Right? Now, in the same sense, remember what kinetic energy is. Kinetic energy is the energy an object possesses due to its motion. Right? So the fact that you apply a force and the object displaces, right? So as it moves from where you push it to where it lands, right, there is also a change in kinetic energy. And that is what the work energy theorem essentially states. That the net work done, right, that the net work done of an object is equal to the change in the object's kinetic energy. Right? And how we express that mathematically is you have the net work done, right? So this stands for net work done is equal to the change in kinetic energy. That is essentially what the work energy theorem states. So even if you forget how to put this in words, right, you are able to put it in words by just looking at how we express it mathematically. Right? Work energy theorem states that the net work done of an object, or the net work done on an object, is equal to the change in the object's kinetic energy. Simple enough. Right? Where W net is the net work done. And remember that the general formula for work done is force times displacement. So bearing that in mind, to calculate the net work done, the force would be the net force times the displacement. Right? And then as far as the change in kinetic energy, the general formula for kinetic energy is half mv squared. So to calculate the change in kinetic energy, it will be the final kinetic energy minus the initial kinetic energy. Right, so the V stands for final velocity minus, and then the U stands for initial velocity. Right, remember, because we're looking at rigid objects, the mass will remain constant. So the only quantity that can change is the object's velocity. So in terms of the change in kinetic energy, right, that is why we have half mv squared, the V which stands for final velocity, minus half mu squared, the U which stands for initial velocity. Right, therefore meaning work net, or the work energy theorem, being expressed as W net minus the change, or is equal to the change in kinetic energy rather, can be expressed like this as well. Right, F net times the displacements, this stands for net work done, is equal to this which stands for the change in kinetic energy. Right, and you can use this formula to calculate any one of these quantities. Right, now let's look at power. Right, power is in watts. Right, the W stands for watts. Right, that is the unit of measurement for power. And how we define power, or how you can define power, is power refers to the rate at which work is done. Right, that definition we can get from the general formula for power as well. Right, power, so the P is what we use to denote power. P stands for power is equal to the total work done, so WT stands for total work done divided by time. Right, putting this formula in words, we would say the rate at which work is done. Right, that is essentially where the definition comes from. So if you forget it, if you forget how to put it in words, right, you can use the formula to assist you. Right, so this is where P is the total power in watts. W sub T is the total work done. Right, and work done is in joules, and the T stands for time in seconds. Right, now this here is another formula we can use to calculate power. Right, where P still stands for total power is equal to F times V. Now the F is the total force applied, and the V stands for average velocity. Total force applied will be newtons, and VAV or V sub F is the average velocity in meters per second. All right, now from kinematic equations, we know that the average velocity, right, when you're just looking at final and initial velocity, the average velocity will be equal to the initial plus final divided by 2. Right, so this is another formula you can use to calculate power. Right, now just take note of this, that in terms of work done, right, if you have a force, there is always going to be some work done due to that force. Meaningly, if you have F net, right, it means you will have W net. If you have total force applied, you will have total work done. If you have frictional force, then you will have work done due to friction or work done to overcome friction. If you have a component of the weight that is parallel to the plane, you will have work done due to that force as well. Right, so that is to say, these are just some of the ways you can express work done, and how you express work done will be due to the force that you are going to use. So if you're going to use F net, it means you're looking for the net work done. Or if you're looking for net work done, then the force you use is the net force. And if you're looking for the total work done, then the force you're going to use is the total force. If you're looking for the work done to overcome friction or work done due to friction, the force you're going to use is the frictional force. Right, so that is to say, there is always a relation between the work done that you're looking for and the force you're going to use. Right, now for dynamics, right, because this section is based on dynamics, right, where we look at the forces that influence the object's motion. So remember, in the first part of module 1, or in the first part of motion, power and energy for engineering science N3, right, we look at kinematics, right? Kinematics, which is essentially a branch of mechanics where we look at the object's motion without looking at the forces that cause the motion or that influence the motion. Right, now we're looking at dynamics, and with dynamics, that is when we look at the forces that influence the object's motion. Right, and how we look at those forces is based on along which plane that the object is moving. Right, the object could be moving along the horizontal plane, it could be moving along the vertical plane, but it also could be moving along the inclined plane. So we're going to look at the forces, right? We're going to look at the forces, or how we look at the forces when the object is moving along the horizontal plane, and the forces and how the inclined plane, right, affects the forces that the object is going to be subjected to. Right, so first looking at the horizontal plane, right, say you have an object on the horizontal plane. The forces that the object will be subjected to will be, first of all, the weight. The weight of an object is always acting perpendicular to the ground, always. Right, regardless of the plane where the object is moving, the weight of the object is always acting perpendicular to the ground. Right, and the weight is equal to mass times gravitational acceleration. Right, and then going against or opposing weight will be the normal force. Right, you have the normal force, so these two forces essentially cancel each other out. That is why when the object is moving along the horizontal plane, right, the work done will only be done along the horizontal plane, right, and no work will be done along the vertical plane. Why? Because the two forces, so the normal force and the weight of the object, right, will cancel each other out. So along the vertical plane, when an object is moving along the horizontal plane, Newton's third law of motion is satisfied along the vertical plane. Right, that force is equal in magnitude, is equal and opposite to the weight. Hence, along the vertical plane, Newton's third law of motion is satisfied. Hence, the work done is only able to, or the work is done only along the horizontal plane. Now, as far as along the horizontal plane, say you have a total force applied, right? The total force applied is applied in this direction, so headed in that direction, right? Now, if the force being applied, so Ft, if the total force being applied is able to overcome friction, right, the object will then accelerate in the direction of the applied force. Hence, if you look at the direction of acceleration, it is in the same direction as the force being applied. And then, of course, friction always opposes motion. Hence, if this is headed in that direction, it means the frictional force will be in this direction. Right? Now, there are two ways in which we consider direction as far as vectors. Right? One of the ways is by using the Cartesian plane, right? Using the Cartesian plane, that's the y-axis, that's the x-axis, right? Up on the vertical plane we take as positive, down we take as being negative, right? Going to the right or going east we take as being positive, and going west or going left we take that as being negative. Right, so that's one of the ways in which we can consider direction as far as vectors. Another way is by looking at the direction of acceleration. Right, we say that the forces going in the same direction as acceleration, those you take as being positive, and the forces going against acceleration, those forces you take as being negative. So that is to say, if you have this scenario where you have a total force applied and the object moves in the same direction as the total force applied, the direction of acceleration will be this one, and the direction of the frictional force opposing motion will be this one. And then the vector sum of forces, the vector sum of forces is F net, also known as the resultant force. Right, the vector sum of forces, which is F net, will be equal to, now remember I said the forces going in the same direction as acceleration you take as being positive. That is why Ft is positive. And then the forces going against acceleration you take as being negative. Hence, as far as the vector sum of forces, for this scenario, it will be Ft minus Fr. Right, well, of course, F net is the resultant force or the vector sum of forces or the net force, and Ft is the total force applied, and Fr is the frictional force. Right, that is how we consider forces and the direction thereof for an object moving along the horizontal plane. Now, finally, we are going to look at the forces that an object is subjected to on an inclined plane. Right, now let's turn this object into this plane into an inclined plane. Right, the reason why I wanted us to start here is so that you see what happens to the Cartesian plane. So this here is the Cartesian plane. So the Cartesian plane here is orange. So that's the Cartesian plane. Right, the red box we are going to take as our object, and the white line is the plane. Right, so I want you to take note of what happens to the Cartesian plane as we move this plane to becoming an inclined plane. Right, the Cartesian plane essentially moves with the inclined plane. Right, where you find that the horizontal plane is parallel with the inclined plane, and then the vertical axis is perpendicular to. So this is what we have here. Right, is perpendicular. There we go. Right, so as you saw there, as we move the plane from horizontal to inclined plane, the Cartesian plane tends to move with the plane as well, such that the horizontal axis is parallel with the inclined plane, and the vertical axis is perpendicular to the plane. Right, Right, so here we have an angle theta. We have an angle theta at that point. Right, now we're going to look at the forces that the object is subjected to when it is on an inclined plane. Right, first let us look at the forces that we have even before, or the forces that the object is subjected to before there's even an applied force, or before a force is applied. Right, so we have, remember I said the weight of the object is always acting perpendicular. Right, it is always acting perpendicular it is always acting perpendicular to the ground. Right, remember this here is now the ground, and that's the inclined plane. So you will have the weight being perpendicular to the ground, so that's the weight. The weight is equal to mg. So the weight is always acting perpendicular to the ground, and then you have your normal force. That's your normal force. Right, the normal force always acts perpendicular to the plane. That is why I draw it here parallel with the vertical plane, or the y-axis. Right, now if you look here, the normal force is parallel with the vertical plane, but if you look at the weight of the object, which is still perpendicular to the ground but relative to the Cartesian plane, right, it is making an angle with the Cartesian plane. Right, it is making that angle with the Cartesian plane, which means the weight of an object, when the object is moving along an inclined plane, the weight then becomes an oblique force. Right, oblique forces are forces that are making an angle with the Cartesian plane, or are forces that are neither parallel with the x-axis or parallel with the y-axis. Right, they are neither, so oblique forces are neither parallel with the horizontal plane or the vertical plane. So as long as a force is making an angle with the Cartesian plane, it makes it an oblique force. Right, and then in applying conditions of equilibrium, we are not able to use oblique forces, because remember, conditions of equilibrium are based on forces that are either along or parallel with the x-axis or parallel with the y-axis. Right, the conditions are sum of forces in the x direction, sum of forces in the y direction. So in applying conditions of equilibrium, we are only able to use forces that are either parallel with the y-axis or parallel with the x-axis. So what we do to oblique forces is we have to resolve them into their components. So that is to say that, seeing that the weight, when the object is moving along an inclined plane, the weight becomes an oblique force, it means we have to resolve the weight into its components. So we are going to resolve the weight into its horizontal component as well as vertical component. All right, starting with the vertical component. So you have a vertical component there. All right, that's the vertical component, and this here is the horizontal component. Right? The vertical component is perpendicular to the plane. The horizontal component is parallel with the plane. Right? You will see sometimes the vertical component is referred to as the weight component perpendicular to the plane. Right? And the horizontal component of the weight is sometimes referred to as the weight component parallel with the plane. Right? So this we call the weight component parallel with the plane, and this one we call the weight component not parallel with the plane. This one is perpendicular to the plane, so you have that, and this one is parallel to the plane. Right? Now, in terms of the angle we use, right, we need to define what this angle is. Right, the angle at this point. Right, in order to do that, right, we are going to draw this right angle triangle. Right, we are going to zoom into this right angle triangle. So what you have there is this essentially. So you have that. Right, and that's the angle we're looking for. Right, this is what we have. Right, this angle represents that one. Right, this here is the triangle we're looking at. Right, that's the angle we are looking for. Right, this is just essentially a zoomed view of what we have here. Right, and then right, this is what we have. Right, the part I just drew is this one. Right, where this angle is equal to theta, that's 90. Right, now 90 minus theta gives us that angle. Let's call this angle, call that beta. Right, so this angle is beta. 90 minus theta gives us beta. Right, now the reason why I drew a picture, a much larger schematic illustration of this triangle is so that you understand where this angle comes from. Right, so if this is beta, it means this angle here is also beta. Why? The two angles are vertically opposite, so this angle is vertically opposite with this one. Hence, if this is beta, it means that's beta. Right, remember that this here is at 90. Right, now if 90 minus theta gives us beta, it means that 90 minus beta gives us theta. Right, that is to say that 90 minus beta gives us theta. So that angle is equal to theta. This angle here is equal to theta. Right, and we've just proved how that angle is equal to theta. Right, so if that angle is equal to theta, right, it essentially means that the weight component that is perpendicular to the plane is adjacent to the angle, and the weight component that is parallel with the plane is opposite this angle. Now, how does that help? It helps in figuring out which trig ratio we are going to use in expressing these components. So this component, because it is adjacent to the angle, it means here you are going to use cos. So mg is the force, cos theta, right? And then this component is opposite the angle, so for that one you use sine. So the weight component parallel to the plane, the force is the weight, so mg, and then because the component is opposite the angle, we then use sine theta. Right, and this is what you get. Right, so before even applying a force, right, to move this object, say up the incline, these are the forces that this object is subjected to. Right, so it is subjected to the normal force, it is subjected to the weight component perpendicular to the plane, it is subjected to the weight component parallel with the plane, which is this one. Right, and then if a force is now applied, so you get a force going in that direction, so you have Ft that is applied in that direction, right, and the Ft is enough to move the object up the incline, right? If that's the case, it means that the acceleration will be in that direction, and as the object moves up the incline, because the motion is in that direction, it means the frictional force, which always opposes the motion, will be in this direction. So here you have the frictional force, right? And these are the forces when the object, or when the force that is being applied is such that the object is moving up the incline, right? That is how you get these forces, right? After getting these forces, you then have to now establish the vector sum of forces. Vector sum of forces is F net. F net is the vector sum of forces, or the resultant force. And how you get the vector sum of forces F net is by using the direction of acceleration. The forces going in the same direction as acceleration, you take them as being positive, and forces going against acceleration, or the direction thereof, you take them as being negative. So Ft going in the same direction as acceleration, we're going to take as being positive, and then the frictional force and the weight component parallel with the plane, because they are going in a direction that opposes the direction of acceleration, we are going to take those as being negative. So that is to say, F net for this scenario will be Ft minus the weight component parallel with the plane minus the frictional force. Right, free body diagrams are very important, people. So this here represents the free body diagram of an object moving up an incline. Right, free body diagram give you context as to the forces that the object is being subjected to and the direction of those forces. The direction of those forces relative to the direction of acceleration will essentially give you the vector sum of forces. Right, so for problems based on forces, mass, and acceleration, always draw the free body diagram. Be it you're looking at an object moving on an inclined plane or an object moving on a horizontal plane. Right? I really hope you found this lesson helpful. Right? It is going to be critical when it comes to exercises based on the application of Newton's laws of motion. Work done, energy, power. Right? Right. Stay tuned for more lessons on engineering science. Cheers.